Hello, my name is Chongwei Lin. In this talk, I'm going to present a Laconic private set intersection protocol from Pairings. This is a joint work with Diego Alania, Claudio Orlandi, and Mark Simkin. Let's quickly recall what private set intersection protocol is. In the two-party protocol, Alice and Bob hold their private sets and want to jointly compute the intersection without revealing any other information. For example, they want to find their common friends here, but do not want the other one to know other contacts in the address list. Recently, private set intersection has been applied in many places. For example, Apple and Microsoft use this for password monitoring to check the safety of users' passwords. Signal used this to enable users to see their friends on Signal without revealing their contacts to Signal service. Also, it can be used for botnet detection, online advertising, and contact tracing during the pandemic. We should note that in the real world, the two parties in these protocols are the client and the server, where the client may have a small set, while the server has a huge set, say all the users' account information. Client-side devices are often resource constrained, and it's not realistic to require them to download the large amounts of data or to perform intensive computations. So we need to make the overhead of the party holding the small set, which is the client here. An emerging field within cryptography asks the same question, that is Laconic cryptography. Here, protocols are run between a receiver with a large input and a sender with a small input. The protocol should only have two messages. The first message can be reused by multiple senders, and the size of the first message is independent of the size of the receiver set, which is the huge set here. The size of the second message is linear in the size of the sender set. Recently, there are many research works for unbalanced PSI protocols. Some are from FHE or introduce a receiver-side storage or require several runs. In this work, we focus on accumulator-based protocols, which can lead to Laconic protocols. The work from Artemisa, Di Cristofaro, and Sudik in 2011 is with private setup, so it's not Laconic. The work from Alamati, Branco, Dötling et al. In 2021 is Laconic, but they don't have a public implementation. We will focus on those two protocols and also compare ours against the state-of-the-art protocols like Rusolek and Zhou in 2021 and Tong, Moreno, Da Gama et al. In 2021 during our implementation. So in this work, we propose a new Laconic PSI protocol from Pairings. And for the first time, we evaluate Laconic PSI protocols by implementation and optimization. We show that ours performs better than other Laconic PSI protocols. Before showing the construction of our protocol, I just want to remind you of the four algorithms of an accumulator scheme. They are setup algorithm, accumulate, which takes the set as input and outputs an accumulated value. And that is a single value, so you can think it's like hashing a set here. Then we have weightness create algorithm, which generates a weightness for an element xi in the set X. The last algorithm is verification algorithm to check whether width is a valid weightness for xi. If so, xi is in the set. Now I will show how to use the accumulator scheme to construct the PSI protocol. For simplicity, we consider private set membership test, that is a PSI protocol where the sender only has one single element in his set. We use the setup algorithm of an accumulator scheme as the trusted setup phase. Then the receiver accumulates his set and sends the randomized accumulated value to the sender. The sender accumulates her W randomized by a random T and sends back along with a target value. Finally, the receiver creates a witness for each element in his set. Here, the witness is an accumulated value of the set except the element xi. Then he checks whether W is just the xi, which is a member in the accumulator. Here we can see this as a variant of the verification algorithm of an accumulator scheme. Now let's see how we construct a PSI from pairing-based accumulators. This is a simplified version with semiontic security and from symmetric pairings. In the setup phase, instead of including the secret S in the CRS, we publish G raised to all the powers of S here. Then the receiver accumulates the set into a single group element. Here, the capital P is the evaluation in S of the polynomial whose roots are all the elements in X. We notice here, the receiver does not know S, but he can still evaluate this polynomial in the exponent using the elements from the setup. Then the sender just accumulates and randomizes W. Finally, the receiver uses pairing and the elements sent by the sender to reveal whether W is in the set X. And to achieve efficiency, we use asymmetric pairings in our actual protocol. We refer you to our paper for details. Now let's talk about our implementation. We first compare our work with other PSI protocols from RSA accumulators for equal set sizes. Here are the numbers for computation by both sender and receiver. We show that ours is faster than ADT plus 21, both for sender and receiver. And with ADT 11, which is the protocol with private setup, our protocol is around 3 times slower for the receiver due to the private setup. That is a rate quite similar to the speed up on the sender side. Here, this is a trade-off which is quite acceptable in Laconic cryptography. And we also compare ours with RT21 and CMDG plus 21, which are the state-of-the-art protocols. We show the sender-receiver latency and communication complexity here. We can see that with RT21, with the size of the receiver set growing, the constant communication complexity for the sender in our protocol starts to pay off, and the sender latency is becoming lower. So ours is more efficient than RT21 in terms of sender latency for the unbalanced sets under the strict bandwidth constraints. And with CMDG plus 21, we can see that ours performs better in the terms of communication complexity and sender latency, especially under the worst network conditions. Well, that is all for our talk. We show that a Laconic PSI protocol can be constructed from some secure accumulator schemes, and ours from Pairings is the most efficient one to date. Thanks for listening, and hope you will enjoy our full version on ePrint.